Welcome to the second week of lectures in the NMR spectroscopy course. In the previous week, we had understood some very important concepts. And since we restrict ourselves to the spin-half systems, when the spin quantum number is half, the allowed states are plus minus half. Both of these states are actually degenerate in the absence of a magnetic field, but when a magnetic field is applied, they end up being non-degenerate. So in this condition, we were able to understand the energy difference would be given by minus gamma B naught, of course with a H cross, which is defined as H bar omega. This omega naught is defined as the Larmor precession frequency. Now we will take a closer look at what is this motion called precession. If one understands the term precession, most of NMR would be easy to understand as we go forward. For these two states, we also saw the orientation that they would be in. We are talking about the B naught that is applied along the z-axis. As these are all magnetic dipoles, the energy would be different for these two states, with alpha being the more stable state than beta, the reasons for which we saw last week. We also quickly looked through the aspect that although the z projection is certain, the x and y components cannot be accurately determined. So this is where we had left off. Let's take a moment to understand what this means. You could either be looking at a single spin, single isolated spin. So what do I mean by that? Let's say a single molecule of water, we are looking at the water protons. Single isolated spin as a function of time. This just means that at a certain moment you might find the spin there, some other moment you might find it there, and at some other instant you might find it here. Remember, I'm only talking about the alpha state. It can keep switching between the alpha and beta state, a single isolated spin as a function of time. But then the probability of finding it in alpha state is slightly more than that of the beta state, which we saw from the Boltzmann's distribution. So what this finally results in is that it will be a cone that this inscribes. So meaning that these spins end up having a motion, something of this sort. This can also be visualized in a different way. That is, instead of having a single isolated spin as a function of time, you could have an ensemble of spins at a given moment. So then what ends up happening, whatever you end up seeing as a function of time, you would be having at every given moment of time. Of course, P alpha is still greater than P beta. Remember, we are at equilibrium. What this results in is that either you take the first picture as averaged over time, or the second picture, which is an ensemble of spins. We can end up resolving each of this given spin to its mutually orthogonal vectors. And similarly, for each spin that is present in this ensemble, one can end up resolving them into its mutually orthogonal component. So when you do something of this sort, where you take each spin and then resolve them into its mutually component vectors, you're going to end up getting something like this. Where in the transverse plane, all possible orientations end up coming as you resolve each and every vector, and all of them add up together along the longitudinal axis. Longitudinal axis meaning the z-axis. When you repeat the same exercise for the beta spin, you would have the same type of random phase that ends up coming with the longitudinal, something that's pointing along the z-axis, adding up. Due to this, the vector sum of anything transverse goes to 0. But on the other hand, all the longitudinal ones end up giving a magnetization. Since the population in the alpha state is more than that of the beta state, the length of this vector will be slightly greater than that of beta vector. So therefore, the magnetization, the bulk magnetization that ends up in this case would be something like m alpha minus m beta. So NMR is all about how do we perturb this tiny bulk magnetization that we get. Remember, this comes up due to the population excess in alpha state versus the beta state. How this can be manipulated in order to get the information that we want about the system. So I am redrawing how the bulk magnetization looks, and remember the B naught is applied along z-axis. From now on I might not be writing this all the time. This will be understood. Whenever you have a vector in a given field, it experiences a torque. The torque is given by the cross product of the vector to that of the force that is applied. And in our case, the vector we are talking about is the bulk magnetization m0, and the force that we are talking about is the magnetic field. For now, it is easy for you to imagine that the field that you're applying is just the main magnetic field B0. As we go forward, we'll have other magnetic fields that would end up coming. So therefore, for our scenario, you can write the torque will be given by m cross b. The vector that results from the cross product will be perpendicular to both m and b. And to start with, let's say we have magnetization, which is m0 of k, remember it's along the z-axis, cross product of b, which is also b0 along z-axis. K cross k is going to be 0. So basically, this magnetization does not experience any torque because the magnetization and the field are parallel to one another. And this is a problem because if you would like to detect this magnetization, you need to have something that changes as a function of time. As we know that if you have a coil, it can only pick up something when the magnetization changes as a function of time. Okay, since we are talking about time here, we need to see how torque relates to time. Classically, torque is also given by the rate of change of angular momentum. And in this case, we are talking about the bulk angular momentum. So I'm going to be writing as dj over dt. And similar to the fashion that our mu is given by gamma I, bulk magnetization is going to be given by gamma times j. You therefore end up having dj over dt is given by m cross b. And then let's say we multiply both sides by gamma, then this ends up being dm over dt, which is equal to m cross gamma b. Remember, for the sake of brevity, I am simplifying m of t and b of t as m and b itself. So this is an important equation for us to consider as we go forward, meaning that the rate of change of magnetization is kind of given by a cross product between m and b. So this also says, since in the case that we just considered a moment back, m0 and b0 are parallel to one another, there will be no change in dm over dt. Since dm over dt is 0, we will not be able to get a signal. Okay? So now what can be done? One thing that can be done is that if somehow we are able to get m0 along the transverse, either x or y or in the xy plane, then m0 becomes perpendicular to that of b0, which is where the cross product is maximum. So how will we end up achieving it? When you apply an RF pulse, m0 ends up tipping to the transverse plane. In this case, I'm giving an example where it goes along the x-axis, but it could be along anywhere in the transverse plane. The RF pulse is nothing but another field B that is applied perpendicular to m0. So let's say we are able to apply a B1 field, or we can call it the BRF field, that's perpendicular to m0, then that will result in m0 being tipped away from the z-axis. So let's say that now we have generated the magnetization now along the x-axis. So now magnetization vector is going to be given as m0 along I. And after we have applied the RF pulse such that our magnetization comes along the x-axis, we turn off this RF field. Of course, we are assuming that when we apply the RF field, the B0 is not present. We will see how all that can be achieved. But for now, it suffices to understand if you are able to get an effective field that's perpendicular to m0, you will be able to tip m0 away from the z-axis. And for this example, we have taken in such a way that m0 is along the x-axis. And when you turn off this RF field, you end up getting the dm over dt as a cross product of mo times I, m0 times I, cross b0 times k with a gamma that goes up front. And we know that I cross k is minus j, so you end up getting gamma b0 m0 along j. The bulk magnetization that is along x starts to move due to the B0 field to minus y. And now after it has reached minus y, You can continue to do this calculation and you will see it will end up along the minus x-axis followed by y and so on. When you have a B naught that is along the z-axis, your magnetization vector keeps going around about the B naught axis. So this motion is actually what is called as precession. Now we are seeing precession of magnetization. Now let's assume that we are able to keep a coil along the transverse plane. This magnetization keeps cutting this coil from which we detect our signal. And how will the signal look? Let's try to plot it as a function of time. And you are trying to plot signal. So let's say it's mxy, meaning that the signal that you get from the transverse plane. It's going to approach, go away, and it keeps on happening. Therefore, you are going to end up getting a signal. It's oscillatory in nature. But of course, it's a little tedious to keep looking at this precession motion, largely because it's going to be constant based on the magnitude of B naught that has been set. So therefore, it is indeed helpful such that we go to a frame which is a rotating frame, where let's say that's a frame that runs along with the Larmor precession frequency. What will end up happening in such a case? So I'm going to say this is the rotating frame. In such a case that you are actually going into rotating frame that you correctly set to omega naught, where omega naught is minus gamma B naught, then you will have a magnetization that only stays along x. Now, let's say you acquire the signal as a function of time, let's say mxy, you're going to get a constant signal, assuming things remain as they are forever. But that is not true, because you achieve this state by disturbing the equilibrium state. So let's try to go back and visualize what was the equilibrium state. We said equilibrium comes up due to population difference between the two states. So therefore, you have the alpha and the beta states, where n alpha greater than n beta, therefore you get m naught due to that. This state has no phase coherence. All the transverse magnetization vectors cancel each other. On the other hand, what the RF pulse achieves is that it equalizes the population across these two states. However, it generates something called phase coherence. In the equilibrium state, you had every possible orientation along the transverse axis, but there's a population difference along n alpha and n beta, therefore you get a magnetization. In this case, you have bunching of vectors, meaning that all the alpha and beta states end up coming together, and therefore, although their population is same, so the vector that ends up coming would be same on either side, resulting in a net magnetization that is along the x-axis. So therefore, in this case, you have no phase coherence, all the vectors that cancel each other, but in this case, you would end up having a phase coherence that is present, the populations being equal. I hope you are able to appreciate the fact that you were at equilibrium and now you are in a non-equilibrium condition. Whenever you are in a non-equilibrium condition, you would like to relax back to where you were. The populations slowly revert back to n alpha being greater than n beta, and the phase starts to decohere, meaning that they start dephasing from each other to go to a random phase that existed in equilibrium. As you are able to understand, the return of a non-equilibrium state to equilibrium state for the longitudinal magnetization, which is along z-axis, is due to population difference, and the mechanism of the loss of transverse magnetization is due to loss of phase coherence. So these two are very different processes, and therefore the return of mz is characterized by a constant called T1 relaxation, which is called as spin lattice relaxation, and the return of mxy to its equilibrium, which is random phase, is characterized something by called spin relaxation. These two are different mechanisms and will result in different time rates for the return of the equilibrium. Slowly, as a function of time, the magnetization that was generated in the transverse plane goes towards its equilibrium value. Similarly, let's plot the longitudinal magnetization. Remember, the zero time is after application of RF pulse. That got our magnetization along the x-axis. On the other hand, if you're looking at the longitudinal magnetization, immediately after application of what we call as a 90-degree pulse, because you started from z-axis and completely went to the x-axis, you would have zero magnetization or zero polarization along the z-axis, but over a period of time, it starts to recover. And this decay rate, we will see in a moment, has an exponential, mono-exponential decay, where R2 is the rate constant of T2, meaning that this can also be written as T over T2. The recovery of this will go as 1 minus, where the 1 will be the, we have to say mz over m naught, because that's our normalization, minus T by T1 type of an equation.